Hello again. Tonight we're going to talk about the fact that there is a gap in the various sizes that are defined for black holes. So black holes don't come in all known, all different sizes. There are distinct sizes to black holes, and then there are gaps. I was watching a video that Dr. Becky did on her YouTube channel, and fascinating as always, and it's good to see her back on the air. But she was talking about this gap, and she tried to describe what the gap was and the fact that there are some recent papers that have come out that are trying to say they think they found an intermediate size black hole, but they're not sure, hasn't been peer reviewed. And then she went on to describe how it's really difficult to find intermediate sized black holes that are not at the center of a large galaxy and not consuming things because they don't put out photons that you can detect. If you look at the range of what happens when a star gets at the end of its life and it transitions from whatever it is to shrinking down to a white dwarf or a neutron star or a particular kind of neutron star, quark stars, or supermassive black holes, then you'll notice that there's a progression there, depending upon how big the star was before it started end of life and shrinking down. But it becomes pretty obvious that they don't come in all possible sizes. There's not a continuous range of sizes. There's sort of distinct size values, and then there's gaps. The biggest gap is the intermediate size black holes. And I said, well, I think there's something analogous here, much like if you said, I'm looking at an atom and the electron orbits around the atom, how come the orbits are not at all possible distances from the nucleus? They're at very distinct, defined, or integral distances, and they actually have letters Q, P, O, M, N, M, L, and K from the inner to the outer. So why shouldn't the same thing be true of the energy of black holes making the size of them? So I just said, well, maybe there is. Let's take a look at that. So you've probably seen the standard model of particle physics. This is kind of the upper left-hand corner. These are all the quarks. The copy and paste of their chart would have come out really fuzzy, so I hand redid this particular section of it. It shows all the different types of quarks or the flavors of quarks. And notice the number in the top left-hand corner of each one of those purple rounded squares. That's the energy level or the mass as defined by energy of the individual quarks. And you'll notice a little squiggly in front of the number as these are approximate. They aren't precisely these numbers. They are within a certain amount of leverage in these ranges. They're distinct ranges. Notice that they're distinctly different values, and notice that they are a range that goes from like 2.2 million electron volts. That's what the MeV stands for. The per speed of light squared is just a standard unitization of it. But notice that it goes from 2.2 million up to 173.1 billion. And there's only 6 types. So they aren't uniformly distributed. There are gaps. They're not equal steps. So I put them into a chart and said, okay, if these are the levels, then what would be the separations? What are the gaps? And just to throw in another particle, if you don't have enough energy to become a quark, but you're involved in stellar degeneration at the end of the life of a star, we have white dwarfs, and then we have neutron stars. Well, neutron stars are made up of neutrons, so if we throw neutrons into the lowest end of this gap, free neutrons energy is 0.782 million electron volts. So it fits nicely at the bottom or the lowest energy level. You now have neutrons, up and down quarks, strange quarks, charm and bottom quarks, and then top quarks. And you'll see that there are energy gaps between these. And between charm and bottom and top, you'll see there's an enormous energy gap of 168 giga electron volts. So I just said, well, that seems to follow nicely with this intermediate black hole gap. So here's the stellar mass chart. You'll see on the left side, white dwarf, which is if the sun at the end of its life, billions of years from now, not anytime soon, collapsed down, it would likely, because of its mass, fall into the white dwarf category. So we'll just mark that one as 1. And then you go up from there as to the mass or the equivalent energy of the resulting collapsed stars. And you have a neutron star, you have a stellar mass sized black hole, and then you have this gap of intermediate black holes. And then you have these supermassive, the ones that are at the center of galaxies, and those can get to a million plus times. There's no, I mean, there's theoretically defined limits of how big a black hole can get, but they're finding that the theoretical limit doesn't match the observational reality that they're seeing. But there's this very wide gap of intermediate sized black holes. So this looks to me like the gap that you see in other things in physics. So why wouldn't that be the case? And so I just postulated the gap in energy of subatomic particles is related to the gap in black hole sizes. So is there a correlation? So I've got a list at the bottom. So if you're less than a white dwarf, but you're greater than a white dwarf, but less than a neutron star, you're probably something that's optically detectable, very easy to spot. The moment you become a neutron star, you're not so easily optically detected, but you can be detected in X-rays and things like that. And then you get to the up and down quark to strange quark range, and those are also high energy particle detected, but they're the lower energy quarks. And then you move up into the strange to charm/bottom, and these are not quite so easily observed because they lose the visible aspects, and they get up into when they start to merge. You can see them in gravity waves. When they when they eat things, they'll put out radiation. Other than that, they're hard to observe. And then you get to actual supermassive black holes at the center of galaxies. Well, when they're supermassive and they're at the center of a galaxy, they're really easy to spot because you look for the galaxy. If you want to spot the black hole itself, I think it took 27 years to spot the precise location of the black hole at the center of the Milky Way. They didn't observe the black hole. They observed all the stars that were in close orbit around it. And based upon the looping of the orbits, they said, well, the mass that it's going around is right here. And they looked at another star, the mass that it's going around is right here. And once you triangulate a number of those stars orbiting this thing that you can't spot, that must be where the black hole is. Yeah, it's easy to spot black holes when they're feeding or when they're part of a supermassive at the center of a galaxy. But that intermediate size where they're not neutron stars and they're not supermassive black holes yet, and they're bigger than stellar mass black holes, but we can't observe them because they're not consuming and they're not at the core of a galaxy. So that's why I'm saying that I think these are probably moving up the quark flavor ladder. So I've previously done a video, you can go see it on the Broader Astronomy YouTube channel, that I think that the top flavor of quark stars are what black holes are. And I've also previously done a video describing a Feynman diagram of photon-photon interactions. Turns out that if two photons hit each other, and this is extremely rare but can be greatly induced by extreme gravity, like very dense stars, then a photon colliding precisely with another photon produces antiparticles, but it does not produce any photons. So if you have two photons go into a photon-photon collision, there will be no photons, no radio, no infrared, no visible, no ultraviolet, no X-ray, no gamma. Two photons that were visible go in, no photons come out. So it may be that the event horizon of a black hole is the point where photons are collapsing into each other and no photons come out. But these recent observations and the analysis of them and what they're postulating is it's not that they can't find the intermediate sized black holes. It's just that they're really difficult to see because they're not consuming anything. They're not putting out any light. And it turns out if you follow the food chain of degenerative star classifications at the end of life, you can go from white dwarfs to neutron stars to various flavors of quarks to black holes to supermassive black holes. And there's this gap between your basic stellar mass black hole and the supermassive ones. And we don't see a lot of those. And why not? And I think it's for the same reason that, we don't see electron orbitals of all different distances from the nucleus of an atom. Based upon the physics, they can only exist at certain spots with no in-betweens. And then links, including Dr. Becky's video. And then the video at the Broader Astronomy YouTube channel. comments, questions?
Yeah, just to clarify, like the sequence between regular star and then starts at the end of its life becoming a neutron star. The limit of becoming a neutron star and jumping to become a neutron star is because of the electric degeneration pressure.
Yep.
So what it means is that if you have a star that just died and the core collapse, it can only be about 1.4 solar masses. If it's larger than that, the gravity is so strong that it's gonna crush the repulsion of electrons. So like I don't feel my finger because the electrons of one side of my finger don't like to touch the other one. So it feels like I'm touching my skin, but I'm not really. It's electrons are repulsing electrons, so there is no real touch anywhere. That's why we don't go through planet Earth because electrons don't like to be close to electrons. So when you get to a neutron, to a white dwarf, all the levels of the electrons are filled and they are close as they can together to a point, and that's because of gravity still kind of holding, pushing down, but that is the electron repulsion that doesn't allow to collapse more than that. But that is a point that you can be heavier than the force that the electrons don't like to be close together. So in that case, you end up destroying the nucleus of the atom and then making neutron stars. So the protons start to absorb uh, electrons and becoming neutrons. And so in that point, you that object needs to be heavier than to become that. It needs to be heavier than 1.4 solar masses, the dead star. And then it becomes a neutron star. That's even smaller. So it's like if you think about it, if a star like the sun, when it collapses, is going to be about the size of the nucleus of the sun, the core of the sun. That's all it's going to left. It becomes like quite big still, but compared to a neutron star, it's going to be exactly the same mass, but collapsed to the size of a city on Earth. It becomes even smaller. And it's so much more concentrated, so much more dense. And then when it gets to 2.7, that is like a range. Heavier than that, the repulsion of neutrons, that like you can crush together all the neutrons together. It's almost like you make one star becoming a ginormous atom that only have the neutrons. They are all so tiny, so crushed together. But you can be stronger than the repulsion of the neutrons. And that's when you end up having a black hole because you're going to destroy the neutrons, and then that is some postulations that you say that when you destroy neutrons, then you end up having quarks. The natural quarks that you see everywhere is up and down quarks because the neutrons is two up and one down. That's why you have neutrons. And then you're going to destroy, end up having a quark star. That's a postulation. It's not proven yet. Some people think that inside of the nucleus of neutron stars, you might have quarks, especially strange quarks. Like there's some stuff that I read, but it's a little bit above my pay grade. I forgot what I read. To compare the size of the stars, the remnant of stars, it's all they do is that whatever resists the fall of gravity. In the case of a white dwarf, what resists the fall of gravity is the electrons repulsing, the electron degenerated pressure. And then in the case of the neutron stars, is because it collapsed to neutrons, it destroyed the atom, and now you have neutrons, and they don't like to go together. So it's heavier than that, then the star is going to collapse until it gets so small, like infinite small. That's what we call it a black hole. So then that's what we have the limits of that only for those stars. And then this like compare what the make them to the gaps that you find in the sizes of those objects. I don't see correlation because when it gets bigger than like quite bigger than a neutron star, like quite heavier than a neutron star, is going to collapse directly to a black hole. Some people think that like super big, massive black hole in the middle of galaxies, some of them actually collapse directly without forming stars from the pictures we are getting from James Webb, like very far away, just brand new galaxies that should not exist. So what they think is the central black hole didn't collapse from a star, but collapsed with so much matter close together that instead of forming star, forming directly a black hole. So that's some of the ideas that the super big ones, or like black holes start colliding with others in the beginning of the universe, and some of the galaxies collide, and now that's why we have the ginormous black holes. And that's why we have the normal regular black holes is remnant of supernovas that we have in our own galaxy. Now, I cannot see the correlation of the size of the particle with the size of the objects.
Not the size of the particle, it's its energy level per particle.
The energy, yeah, I don't see, what the size of what I meant is what the mass of the particles.
And there's no questioning of the stellar progression that you described.
Mm-hmm.
The issue is we have stellar mass black holes and we have supermassive black holes and we have nothing in between. And there's a very large gap between the two.
There's actually an article I forgot to post. There's recent, like they might have found some black holes on the Hubble data, the repository of Hubble data. They might have found some mid-sized black holes.
Yeah,
but I didn't really read. I just found the article. I didn't have time to read.
Well, follow the link at the end. That is Dr. Becky's video as she covers that recent Hubble discovery of an intermediate-sized black hole candidate.
Okay. So are you saying that this information that you gave tonight is we have determined this, or it's a theory?
What part of it? The gap?
Okay.
Yes, the gap definitely exists. Why?
And we knew that.
Yes. Why the gap is unknown. So they're looking for candidates. Well, there can't be a gap if we can find things in the gap. And finding things in the gap are very difficult because if a less than supermassive size black hole that is far bigger than a stellar mass black hole existed and it didn't exist as part of the core of a galaxy, how would you spot it? Because there's no photons coming out of it. No radio, no infrared, no visible, no ultraviolet, no X-ray, no gamma. Now, if it collides with something, you can see gravitational waves. But if it's just
when they are munching, you can only see black holes when they are munching. If they're, satisfied and they have no food around, you won't be able to see them.
Well, if they're munching, you still can't see them. What you're seeing is the gas as it accelerates into the maw. The gas glows in various wavelengths. So you're seeing what's being heated up by it being consumed. The other thing you can see is when two black holes merge, you can see the gravity waves from it, and you don't require electromagnetic radiation to see that. It doesn't glow. It just makes ripples and gravitational waves. If it's not interacting, if it's not eating, if it's not colliding, and it's an intermediate-sized black hole, meaning it's larger than a stellar mass, but smaller than a supermassive, and it's not the core of a galaxy, there's a big gap in there, and we have no peer-reviewed, confirmed observations. I agree that the new Hubble observation looks interesting, but there are not basically corroborating teams on that one just yet.
So you're saying that we may be someday able to see the black hole when it in other time periods when it isn't eating. That's one of the goals.
Well, it's kind of hard to spot a smaller black hole. Let's say you're looking at stars in your galaxy and a black hole passes behind the stars. You're going to see gravitational lensing of the star in your galaxy based upon the black hole gravity affecting the photons on their way to you.
And my galaxy is labeled as what?
Milky Way.
Milky Way, right.
Yeah.
Okay, that's what I wanted to make sure
I
was going on the same one.
If there happens to be
your home sweet home.
Yes, if there happens to be a small black hole in our galaxy and it's passing between Earth and some distant star or galaxy, then it will affect what we see there. So if the black hole passes something either in front of or behind it, then we'll see gravitational lensing. But you have to be staring at whatever you expect to be lensed continuously in order for that brief period in time in which it gets lensed.
Yeah, it's very hard because you have to be looking at the right place in the right time, and they're small, like from the distance that we
And
are.
so if we had a black hole that existed, which we could, right? You're saying somewhere in space in our Milky Way
Yes.
that's between us and another planet, I gather.
Another star.
No?
Another
Another
star.
star. Okay.
Farther
A
away.
star.
Yep.
Okay. So it's between us and other. So we need to know that so we know that we don't want to get sucked in or we need to abandon
No,
Earth
we
or
are in a
something.
safe space around here.
We're just advancing astronomy, and we'd like to know where all the black holes are, just in case.
But I
Yeah,
mean, is
and
there
then
something we could do about it? I mean, is
No.
there
Our
something that
current
this knowledge
technology,
will help us?
our current technology would have absolutely no solution for even a stellar mass black hole colliding with the Earth. The odds are infinitesimally small, but if
and we would have a bombardment first
yes,
Of
there would be
what?
a lot. There would be a lot of
of
debris.
meteors and comets and stuff,
Yeah,
because they would be disrupting the gravity of the outside of the solar system. So even millions of years before the black hole come near us, we're gonna have a bombardment.
So we know right now there isn't a black hole near us because we're not having a bombardment.
Yeah,
well,
Okay.
we know from our observations that there are no black holes close enough to us right now to create a disaster effect. We know there are black holes out there. We know there are black holes in our galaxy. There's a supermassive one at the core, but it's not affecting us anytime soon, except maybe the solar system's orbital speed around the galaxy. But
The
that's
orbital speed around the galaxy, and how's that affecting us?
that's debated as to whether that's dark matter, dark energy, or the gravity of the black hole.
What do you vote for?
I think
that
it's
would not affect much
I think
because we would be moving the same speed as almost everything nearby in the same diameter of the galaxy that we are, because it works kind of imagine a CD moving around. It's the galaxy is almost ridged. It make no sense because it's supposed to follow uh, Kepler Newton of from the distance from the center moving faster and from away from the galaxy moving slower. But it doesn't happen quite that way because of the dark matter. And so basic whatever is in the same distance from the center of the galaxy to us will move in a kind of similar speeds.
Does this help us understand dark matter at the same time?
assuming dark matter is actually a thing.
Yeah.
Yes, assuming that.
It's
Yeah.
called dark because we have no way of directly detecting it.
I mean, you believe there's dark matter, right?
I do.
The verdict is out for me.
Oh, really? Ah, okay,
Hey,
interesting.
that is some massive objects that affect the gravity of objects, not just in our own galaxy, but clusters of galaxies far away. So that's something that has mass, is that's what we call it dark matter, because if it has mass, it's most likely matter. So that's a nickname that we gave to something that is massive, that we cannot see.
We directly associate mass with gravity, and if something is gravitationally affecting something else, there's a presumption that it must have significant mass.
Yeah, so if I'm sitting in a seesaw and the other side of the seesaw is completely in darkness, but my seat is way up and I'm on my legs are dangling, even though I cannot see the person in the other side of the seesaw, I know that person's more massive than I am because I'm dangling my legs on the top.
Or the seesaw is broken.
Or the seesaw does not have a person on the other side. It has a solenoid and somebody energized it.
There you
Oh,
go.
no.
Yeah, it could be.
Yeah. It could be an electromagnetic effect, not having anything to do with mass.
So it's something that we as observe as something massive. It could be another effect, like you said,
Mhm.
that seems to be mass, but for now, that's what we're calling, because we notice that it's the most of the effects that we observe are similar to massive objects.
Yeah.
The only thing is that this object seems to be massive, but it's non-interactive with electromagnetic waves.
And also over the millennia, over the centuries, I guess is a better way to describe it, we have changed our mind as to how much stuff is around us.
Yeah.
Because prior to us detecting and confirming the existence of infrared, things just got hot. Ultraviolet, X-ray, gamma, things in the universe have been pumping those wavelengths out for a long time, and they are just presumed to be so minuscule and insignificant that they have no effect on anything. Well, as we know, solar sails work, they exist. So the whole issue of things that are infinitesimally tiny on an individual basis collectively can produce large scale effects.
Okay. What happened well, not last week. I don't know when you decided to write this article, but something triggered you to write this article. Was there something new that happened that made you think of this, or is this just something that you've been wanting to talk about?
The fact that there is a black hole mass gap between stellar mass and supermassive, I've known about that for some time, and there's never been an explanation for it. There's been a difficulty in observing. That's why we can't find any, because they're hard to spot. And for me, that just means, well, maybe you're not looking in the right way or with the right kinds of instruments or technology. But that's not to say that there isn't anything there. It's just we can't see it. Just like we didn't know infrared was there until we could detect it. Well, this
Okay.
same thing holds true that this week I watched another of the videos that Dr. Becky put out, because she's a black hole theorist. She's basically a professional astronomer in the realm of black hole science.
Uh-huh.
And she has mentioned the black hole mass gap previously in other videos. And as a result of this latest observation coming out, courtesy of the Hubble Space Telescope, some research team said, I think we found an intermediate sized black hole.
And when was that?
That came out a month ago.
Oh, okay. Okay.
And I didn't mention anything about it because I was waiting for a good review of it, a peer review, corroboration, something. So far, there hasn't been, but it was interesting. And when Dr. Becky put out something about it, I said, well, I guess I won't sit on the fence anymore, and I'll just come out and say, yeah, I think I've got a postulation, not a theory, not a formula, but a postulation. There seems to be a gap. There are gaps in other ranges of measurements, and we eventually conclude the gaps are normal for physics. So why wouldn't the gap in black hole masses be normal for black hole particle physics? And if you look at the masses of individual particles on the table of particles, you'll find that there is a significant gap, and they're measured in electron volts, not grams. So it's energy mass relative, that the gap is there. And I said, well, maybe the reason why you have two gaps is they're related, because if you look at the progression as stars get to the end of their life, they go from matter containing neutrons, neutron stars, and then they eventually become stellar mass black holes and then supermassive black holes. And the parallels in distances and gaps between the various values was just too obvious. Yeah, somebody needs to do research on it. Somebody needs to do peer review. That's just my 2 cents worth, that there seems to be something that looks like this. Is there a connection between the two? I think there is. That's just my
the other thing is like with gaps and stuff. So we know that stellar sized black holes are made of because of the explosion of supernovae. And then we see huge black holes, and then we know that's because galaxies collide and they end up growing and growing and getting to the size of can hold a galaxy. And now we are finding another problem with those black holes is that because we are finding huge galaxies only few million years after the Big Bang, and that it gives a problem because it doesn't give time for galaxies to collide to actually form those huge black holes. And so now there is some papers being produced that's saying that some of those black holes actually collapse directly instead of the first hypernovas. They don't even go through that phase of hypernova. It's so much mass in the beginning of the universe that everything collapsed directly to be a larger black hole, and those were the seeds of the first galaxies, even before the clearing out of the fog from the dark ages of the universe when the first stars start to form.
And
So
that's
the idea is that you're having those objects forming like the seeds of the galaxies, even when the clumped gas was close enough. And then the problem is that how can you make up, especially if it's like close to us? It's you should have like multiple different sizes of black holes because it will be the phases of from starting from small black holes colliding with other black holes, or just getting larger and larger and larger as the time goes, and we are not finding that. It's kind of what you shouldn't be like in between sizes, that is in between sizes of everything, and we are not finding it. It's kind of very strange.
and
But maybe it's just because the biases of the way we look at the universe. We might have black holes in between sizes. It's just very hard to observe them, and so that's the bias. Is the technology wall.
and the direct collapse black hole is a postulation. It's not a theory. We presume that's what happened because with the Webb, we're actually seeing fully formed galaxies too early in the age of the universe. We're seeing galaxies that couldn't have gotten to be that large except through mergers. And if they merged that early on and we're seeing that far back in time, then we should not see nicely shaped galaxies. They should be irregular car wrecks. They shouldn't be nice uniform looking things. And so we just say, well, had to be direct collapse, or it had to be supermassives that merged with other supermassives that very quickly settled down and became nice uniform, ellipticals. Those are just all postulated answers for the observations that they're seeing.
I hear that. One of the interesting things also thrown in there recently is the thought that we have biases in science. But in history of biases in science, it's been political, right? I mean, a lot of it, not all of it, but or it's been spirit. The gods had it this way, so you can't look at it differently because God said it was like this, where God didn't say it like that. I mean, as far as my reading of the Bible, it
It's
didn't.
like when we have a wall of difficulties of seeing or observing or understanding, not always is the biases of the mental problem or what you believe or you do not believe or your error in reading. It's also that is a biases in the sample, that is a biases in the technology that we use to collect the data. So we have to actually be able to try to find the errors in our own data. That's hard to find. That's why we call it a peer review, because I write something, I don't see my mistakes. I always ask somebody else to read what I wrote because I cannot see my errors. But
Right.
yeah.
But I also
So,
wonder what is there. Sometimes we know that there are biases going on, and some times we know that those biases are a reflection of a certain group. And I wondered if there is anybody against the, small black hole group or something
Yes, there
that
are.
has
no,
a
it's
bias.
just
yes, there are.
it's a bias
Oh,
in
really? Okay.
observation.
Tell
There, there,
me.
there are groups that don't have an answer for intermediate sized black holes, but there are also the same groups that will say, in order for a neutron star to collapse down to a black hole, even a stellar mass black hole, the numbers need to be the following. And they have formulas, computer simulations, and the like. And the original official number they had is now a range of numbers. It's a small range, but it's a range of numbers. So I always thought of it as whenever science comes up with what they know to be the answer, the correct formula, the only number possible, that's the most difficult part to dispel.
Uh-huh.
So if you want an example of that, there was only one galaxy in the entire universe. That was the Milky Way. Up until the late 1920s, when we finally developed telescopes that were good enough to see other galaxies, and we went, hey, wait a minute, there's a lot of those things out there, and they seem to have structure. Those aren't just simple, massive nebulas of gas and dust, clouds of gas. And they're what we would think of as a galaxy. There's stars in them. So the transition from there's only one galaxy, everything else is a nebula, to there's billions of galaxies. There were people that were for and against it. There were camps. And we finally got past that because there was just so much observational evidence. And I think
it was actually a gentleman called Hubble.
Yes, I think that the things that we think we have a good bead on now in science don't stand too firmly on that ground as our observational technology progresses. Because there was a time when we said, I don't know what, there's 50 million stars in the Milky Way. The current number is over 200 trillion. So, what you think you've got a good beat on in science?
It's between 200 to 400 billion.
Yeah.
Our Milky Way.
Well, there's trillions of galaxies in the known universe. There's hundreds of billions of actually identified stars in just our galaxy. So
and then in numbers of galaxies in the observable universe is around 200 billions of galaxies, but they think that the number is way much bigger is just because in our visual horizon that's what we can see, but it's probably hundreds of million more than that.
There was a recent
90 trillion or something.
There was a recent image taken by the Rubin telescope that was trying to simulate the original Hubble Ultra Deep Field. And the original Hubble Ultra Deep Field had 1,200 galaxies in it. And it was a patch of sky about the size of your little fingernail. If you held it out at arm's length, that was the size of the Hubble, not the original deep field, the Ultra Deep Field. And they attempted to do the same thing. And what they found was there's many, many more thousands of galaxies in that part of the sky than we thought we had a good beat on, because we had a good picture. Now we've got an even better picture, and the number just goes.
How many pixels? I forgot the name. It was like crazy number of pixels.
So what's it all for?
What's that all about, Alfie?
Why? Why is all
42.
That? Nobody knows what it's for.
I know, it's 42.
Yes. The answer is obviously 42. But the question is, if we think we know what the probability of another Earth-like planet is in our universe, not in our galaxy, but in our universe, the odds are almost indisputable one, just based upon the sheer quantity of galaxies, stars within galaxies, recognized planets around stars, stars in habitable zones. It's just...
Yeah, that's what Sagan said. Yeah.
Yeah, I mean, the probability has got to be at least one. Now, the actual quantity, we don't know. But, every time you scale up something by thousands, the odds on there being another Earth just grow considerably. So, the original formula they had factors in it. And the moment that you put any of those factors to be 1.0, the odds of finding another Earth with a sentient life form that's at least at the same level of technology as us or further progressed is 1. Is it a number far greater than 1? We don't have to indicate that because the question has always been, is it 0 or a small fraction or 1? And the moment you take any of those factors and you say 1 is the value for it, 1, yeah, there's other life in the universe. We just haven't talked to them, haven't detected them, but the probability is 1.
I wonder if they have dogs.
No, they probably have targs.
What I'm thinking
They're like Klingons.
Is that we would like it if we found another planet out there that was not inhabited, so that we didn't have to disrupt another culture, and we could go and destroy that planet.
Well,
You know? Hopefully not. Hopefully we would build it up, and people would take into considerations the things that didn't work well here could work differently there would be really great.
One of these star systems that was originally found as part of the Kuiper project that we've looked at in more detail now that we have the Webb telescope and its spectroscopic capability, where you can take the light from a star, have that light pass through the atmosphere of an exoplanet, and you can split that and detect the chemical composition of the atmosphere of that exoplanet. They've done this to the B, C, D stars, B, C, and D exoplanets around the TRAPPIST-1 system. And as far as they've detected so far, each of those exoplanets has no distinctive atmosphere. So there would be
what does TRAPPIST-1 mean? I mean, what was that?
TRAPPIST is because of the name of the survey. They have like cute acronyms for the surveys. Sometimes it's the name of the telescope, sometimes it's the name of just the survey. And TRAPPIST, there's a bunch of planets called TRAPPIST, but then that is they give a designation and a number, and then for you to see the planets in it, they're gonna have letters. So there is quite a few TRAPPISTs. I don't remember the number.
So Monroe, how did you use it in that sentence? What was I supposed to get out of that by you saying TRAPPIST?
The TRAPPIST, TRAPPIST scientific research program was looking for exoplanets.
Okay.
This is the first one they found. It's relatively close to us within our galaxy. They spotted multiple planets around it, around that star, TRAPPIST-1. And the Kuiper program confirmed the existence of not just one exoplanet, but multiple. I think they're up to TRAPPIST-1F now. You should know that the letters don't start with A. They start with B.
Yeah.
The letters are not based upon the relative distance from the star. They are the order by which they were discovered.
Yes.
So, TRAPPIST-1b was the one that's farthest away from this red dwarf star that they could easily spot it with the TRAPPIST system, with the TRAPPIST science program. And then Kuiper came back and confirmed, oh, there's multiple. You know, B was confirmed, C, D, and E. Now that we've got the James Webb Space Telescope, we can see even more exoplanets.
So this TRAPPIST map, right? It's a TRAPPIST map of these different exoplanets?
TRAPPIST is the name of the observing program, the science team with the instrument looking for something.
Oh, okay. I'm sorry, I didn't get that. You haven't talked about TRAPPIST before, have you?
A couple of years ago, yeah.
Oh, a couple of years ago. Okay.
It's been a while.
I can count that for not missing that one.
Yes,
okay.
Yeah, the acronym means Transiting Planets and Planetesimals, a Small Telescope Project. La Silla Observatory.
Yes.
Okay, so there are these people that are observing, but those are in the Milky Way, what you're talking about, those exoplanets, right?
Yes.
Okay. All right.
And they're relatively close to us.
And the TRAPPIST didn't have anything to do with the map, you're saying, right?
No,
okay.
It's not the name of a constellation. It's not
It's
the
a
name of a star. In fact,
it's the name of a
it's,
group of people that are working on these exoplanets
well,
and finding out more
it's the
information.
name of the people plus the instrument that they were using. And as TRAPPIST indicates, it's a small telescope. It's not like, the biggest telescope on the planet. It's a
Uh-huh.
relatively modest sized telescope that professional astronomers were using. And they discovered it. And the first T is transiting. So they were staring at this star. And as the exoplanet went in front of the star, the brightness of the star dipped
Ah.
and went in front of it. It transited, it
Uh-huh.
dipped. And then when the planet went beyond in its orbit around the star, the brightness went back up. So they
Okay.
detected TRAPPIST 1b by the brightness dip of the TRAPPIST 1 star.
Okay. And the significance that they were able to find by doing these testing on it was to find out what kind of gases were there, what
That's
kind of
the latest
minerals.
thing. That's the latest thing. The TRAPPIST
Uh,
program does not have the resolution nor the spectrographic capability to detect atmospheres in these transiting exoplanets, but the James Webb Space Telescope does. So a science team not related to TRAPPIST got some time on the James Webb Space Telescope, and they did spectroscopic observations of three of the exoplanets orbiting the TRAPPIST 1 star. Now, because TRAPPIST 1 is a relatively small red dwarf star, the planets that are orbiting it are relatively close in, so they don't have to wait hundreds of years for that planet to go around the star again. So they can do multiple passes within maybe a year, but they only get a window of opportunity to use the Webb telescope for this. Webb's got other things it's doing. So scientific teams signed up, they got a window, they did their observing, they happened to catch three of the exoplanets go by, and they did a spectroscopic analysis of the light from the red dwarf passing through the atmosphere of each of the three exoplanets. And then they did the spectroscopic analysis. They subtracted out the red dwarf's light and the light that they had left. They could do an absorption spectrum and find out the chemical composition of the atmosphere of those exoplanets. And what they found out was there's no significant atmosphere. They did find carbon dioxide in one of them, but the other two, they didn't find any distinctive absorption indications of any significant atmosphere.
well,
Now,
this TRAPPIST project still exists, right? That originally discovered these exoplanets.
Sure.
and in fact, they actually put up an Earth orbiting telescope to extend the TRAPPIST program. But
And so the TRAPPIST program must have been thrilled with getting this other information.
well, the
I
whole
hope they work together. I hope they work together is what I'm trying to say.
oh yeah, the TRAPPIST team was thrilled, a little dismayed the fact that they didn't find any atmosphere. But remember, they've got two more exoplanets in the TRAPPIST 1 system to examine with the James Webb Space Telescope, assuming some science team booked a slot of time to look at it. Because remember from when I was describing the Webb telescope, it's in synchronous orbit of the Earth going around the sun. So if TRAPPIST is over in a particular direction, there's only a certain number of months during the year when the James Webb Space Telescope can look at TRAPPIST 1. Yeah, everything's got to be lined up. They just missed that window. They're going to have to come around another year from now, which means the next James Webb Space Telescope observing work list. So they can file for time on like the fifth work list or the sixth work list, but they're done with the fourth work list.
That's exciting, and they probably have more people interested in doing this since now these other people have done this other type of data.
Right, right. But now they're trying to come up with explanations as to why no atmospheres. Well, it's a red dwarf and it's very energetic and it produces massive flares, and the flares can extend beyond the orbit of these three exoplanets, and therefore they could have their atmospheres essentially scrubbed away by the plasma discharge from the red dwarf. And, maybe it's easier to spot exoplanets around red dwarfs, but my money's always been find the larger orange dwarf, more stable stars, find exoplanets around them. They'll be further away. The habitable zone will be more realistically safe from emissions from the orange star. And because it's an orange dwarf, it could be about 1 billion years older than our sun, which gives them far more time to progress their technology should they exist. So, it's fun to look in the yellows, and then it's fun to look in the reds. The oranges are the ones you should be looking at, not the reds, not the yellows.
But are they looking at the oranges?
No.
No.
And
Yeah.
it's really obvious that, okay, if you look at the lifespan of stars and you say, what's the theoretical lifespan of our yellow sun? What's the theoretical lifespan of red dwarfs? It's, well, we're good for maybe 5 billion years or so, and red dwarfs are good for maybe upwards of dozens of billions to hundreds of billions of years, which is, that can't be right. That's older than the universe, but theoretically extensive lifetime. And then there's the one in the middle, the orange dwarfs. The orange dwarfs could be 8 to 10
30
billion.
billion years.
They could be 8 to 10 billion years. So if we catch one in the middle, they'll have about 1 billion years head start on us, on Earth. So, if we think of ourselves as we've only progressed in the last 150,000 years to get what we have today, what if you threw in 1 billion years? What if you threw in 500 million years? What if you threw in just 200 million years? How much farther advanced would they be? Presuming they survived their
Presuming that we
technological infancy.
yeah, presumably the great that is a
We
name for
we
it.
either don't blow ourselves up or don't destroy our planet.
So you're saying
Or
100 million,
AI doesn't take over.
so you're saying 100 million years from now, when we still exist, we may have more technological abilities, and you're saying those are some planets that might be out there already that are at that stage.
They have the potential because they're orbiting an orange dwarf, and an orange dwarf can be about 1 billion years older than our sun. So they've at least had hundreds of millions of years more time to advance than we've advanced. And also remember, we're now in our 5th reset on Earth. There's been 4 other times that essentially the population of the Earth has been dwindled down to less than 100,000 people, and then we've resurrected back up from that. And also technology, we're on the 5th time that we've discovered that the Earth is not the center of our solar system. There's 4 other times when we're really sure that the sun revolves around the Earth, or maybe that the Earth is flat. And, we got to get through those periods that occur multiple times. So I think it's going to take us millions of years to really get a good beat on things.
I don't know. We're progressing pretty quick,
Now we've got apps on cell phones.
Yeah. I remember in 1968, they couldn't predict what was going to happen 30 years in the future.
And now, up until recently, we've been able to predict the path of hurricanes.
There you go.
Yeah.
So imagine another 30 years from now, we'll be much more advanced than we are.
Much more advanced. Will we be advanced enough to conquer light speed? Probably not.
And we still have puppies.
Yes, and kittens. Will we be advanced enough to not be dependent upon fossil fuels for energy production or vehicle transportation? The verdict is out.
30 years from now? How far advanced? How many years from now?
I wonder how many people actually consider the breakthroughs that come that we didn't expect. And we've had several unbelievable.
There was an entire TV show by James Burke called Connections where all the things that we rely upon were due to things that we didn't expect when we were doing things.
There you go.
And it's not just super glue or Velcro.
Right, yeah, but they'll still happen in the next 10 years, 20 years, 30 years. There'll be breakthroughs that we're not even thinking about And
If
that'll
we
advance
don't
us.
survive the Great
You
Filter,
don't have to think a million years in the future. All you got to
No,
do
no,
is
no, no. I'm saying if we haven't conquered these things yet, and we know it's going to take time,
yeah.
what if you had an exoplanet where they've had many millions of years head start on us? How much more advanced would they be?
Only if they had our luck.
There's no way to think about it.
Again, it's a matter of luck.
Yeah.
It's a matter of, what you believe in, what your motivations are, who's in power. Yeah, are they authoritarian? Are they, more open to other thoughts? All those things factor into the advancement of a species, which leads us up to the prime directive. I'm sorry, you haven't advanced to the point where you don't understand warp drive.
we are not
Therefore, we're
even
not
on
gonna
level
talk to you.
1 on Kardashev scale.
Yes, we're going to watch you from a distance because we don't want the wild animals down there hurting us. Or, if you keep up with this nuclear stuff, the Earth could be reduced to a burned out cinder. So say we, the advanced folks in the universe.
Or they would be arrogant about us. They couldn't care less about us.
Well, there,
Little ants.
the first Battlestar Galactica series, not the remake, they had a part of the series where they did encounter an exoplanet that had a sentient species that was humanoid that went down a different path. They went down more of a dictatorial path, more of a militaristic path. And it was, now, how do we conquer these guys? And the best answer for that was develop the technology to outrun them and just leave them in the dust. Because you can't convince them of the error in their ways. So sometimes it's just better to progress on your own.
Until we get fat enough for the calling.
To serve mankind. It's a cookbook.
The cookbook.
Yeah. So any comments or questions before I stop recording?
No.
Hearing nothing.